Thanks for coming. I know it's early in the morning, a little early for me, and so I appreciate all your energy. I'm Paul Maddox, and I'm president and founder of Mizar Imaging LLC, and I have a vested interest in what I'm getting ready to tell you. So just so everybody knows. And I'd like to thank a bunch of people here. I don't have time to go through everybody, but we've had a lot of wealth of collaborators to test things and to try samples. Okay, so this is light sheet microscopy, and so this is taken at the Marine Biological Labs where I was a fellow. This is my friend Phil. He's a light source, and that's a cylindrical lens that he's holding, and it creates a sheet, and there's a sample in the middle that gets excited. And so that pretty much wraps it up. If you have any questions, come to booth 330. No, I'm just kidding. So the conventional microscopy uses a sort of a transmission type illumination, and where we illuminate either with a column, a focus column through the objective lens, or a spot focus with a confocal, for instance. Or there are other modes, of course, but I'm just illustrating two. And light sheet illuminates with a sheet which is in the same focal plane as your objective, at the focal point of the objective. And this creates a high efficiency illumination where you don't have extraneous photons entering your sample. So you have every photon that goes in is hopefully creating something that you're getting out of it. And so you reduce the amount of damage on your sample. And so when we started thinking about this, this is sort of drawings stolen from papers and websites, but essentially you have to position your sample at the intersection of two objectives, or a light source and a detection objective, and this creates an interesting geometry where your sample is sort of mounted there in either sort of vertically like this or sort of in a horizontal fashion. The outcome of this is that you need quite a long working distance for the detection objective as well as the illuminating objective, which limits the numerical aperture that you can use. And numerical aperture being the key for resolution in conventional optics, and also for making nice bright images. So it's physically impossible to use a light sheet with a very high NA objective. So I'm talking about an oil type immersion or a water type immersion that uses a cover slip. So over 1.2 NA. And this is illustrated here. This is a CAD drawing of a 60x 1.4 NA objective, and that little red line there is the focal point, and this is the intersection of the optical axes here. And so the working distance of this lens is 170 microns. This distance is a lot larger than that. So this is sort of the problem we had. We want to use this objective with a light sheet. And so that's sort of outlined here. This is with, and so we illuminate the sample. We want to use a light sheet to decrease phototoxicity and to reduce out-of-focus excitation. We want to use our traditional high NA objectives because they have high spatial resolution natively, and they generate nice bright images. And this requires that we use a cover glass for mounting. So this is required for this. Okay, so with Tanner Federo, who was a technician of mine at the time and now a very industrious graduate student, we came up with this. It's LITE microscopy. So lateral interference tilted excitation. I'm going to quickly take you through. I don't have time to go through all the details, and I'll say it now. We're in booth 330, which is just down here, and you could come by and talk to us. We're very happy to go into more details. And so I'm just going to go over why we tilt it. When you focus light with a lens, you need an uninterrupted light path or a homogeneous light path for the rays that focus to a point in order to make a nice focus spot here. And so we use a cylindrical lens to make this, and a sheet, which I don't have exact time to go into that, but this is not novel, or a lot of people do that. But if we make a sheet here with our objective, this is our 60x 1.4 NA objective. This is a cover slip. This is all to scale, by the way. And that little green dot right there is a C. elegans embryo. It's about 50 microns tall. And so the available working distance is 170 microns. This distance is still a lot larger than that. So this just can't work. And so being a biologist, we cleverly tilted the light sheet, tilted the cylindrical lens. And so, so what we do basically is we tilt this lens so that the converging sheet travels parallel to the cover glass and forms a sheet directly over on the cover glass surface. And we can image directly on the surface. We've even imaged single microtubules that are adhered to the surface, and they're about 25 nanometers tall in diameter. So then we can move the sample through this and do sectioning, etc. So I'm going to show some examples now, and so these are single microtubules in a Xenopus laevis tissue culture cell. That's a frog. And so this is a cell that's adhered to a cover glass and sort of an epithelial type cell. And it's tubulin GFP. This is a 10-minute movie. We image every second. This is a 150x 1.49 NA. And there's no processing to this movie. It's a raw piece of data. And you'll see that I change the focus periodically, but that's just because I can't leave things alone. Okay, so this is an endoplasmic reticulum marker from the physiology course, and let's see if I can make this play. And so, so you can see dynamics in here quite nicely. I guess it doesn't loop. And Tanner could probably tell you more about this sample than I can. But yeah, oops, there. So now this is using sort of super res type imaging, where this is a sample from the Vaughn lab at University of Washington, where this is an expanded tissue culture cell with I think it's a ER or mitotracker red and then chromatin here, and then this is again the ER marker, but now processed. So this is the raw image. This is a process now for the SURF, which is a time-based super resolution technology that Ricardo Enriquez sort of pioneered, and I would point you towards his work for more information about that. But so now this sort of doubles the native resolution of this, and so the resolution of this is probably 210, 15 microns, and now we're just down to 100 or so. Okay, this is a syncytial yeast that my colleague Amy Gladfelter works on, her student Therese, and we help them. They're interested in lineaging this the nuclei in this organism. They have differential behaviors, just so one nucleus beside the other one they don't necessarily divide at the same time, and so they're trying to understand how cell cycles are regulated in differential manner in the same cytoplasm. And so it's important for them to lineage. And one little problem is that they often switch positions. So like here, the purple nucleus switches position with the blue one. And so if you don't take images, you have to take images for a very long time to lineage them. And then, but if you don't take pictures fast enough, you can miss some of these switching events, and therefore your lineage is no longer accurate. And so, so we were able to image this for, I don't know, some 7-8 hours, and at high time resolution with a 60x lens, and yeast is pretty small, so you have to really mag up and then lineage these nuclei for them. So here's an example of that. You can watch the nuclei divide and follow its little path there. There we go. So So sort of in summary, I'm going to try to get us back on time here. The lateral interference tilted excitation has advantages of low photo damage but it has also the high resolution of sort of immersion-based optics, high NA optics, and we combine those two to make a light sheet that is both high NA and low photo damage. And it actually fits on existing microscope stands and is on an inverted microscope stand, and it's agnostic to maker, to detector. You just need a stand of some sort. The other sort of benefit of this is that you can mount things in a more sort of normal way that you're used to, and you don't have to. The mounting requirements are a little less stringent. And finally, benefit is that it doesn't require post-processing. The image you get is that the native image is actually your data, and you can just use that. You can, of course, post-process as I've shown, but it's not required. Hello. Okay, so this is our little team here. These people are all here, and including myself. So Joel and Anji and Chris will be at the booth at 3:30, not 3:30 this afternoon, at booth number 3:30. And Jamie, who's our sort of adult in the room, is also wandering around. So I'd like to thank you for your attention, and I hope I got us back close to on time. Thank you.